All right, in this lesson, we're going to start looking at this idea of simple harmonic motion and kind of talk about what it means and give some definitions that are important to talk about when we look at simple harmonic motion. First of all, when we talk about simple harmonic motion, that's really any type of motion that's repeated over a regular time interval. And it's a type of motion that happens over and over and over and over again. We've already seen some of these types of motion, something like a planetary orbit or any type of circular motion where an object is moving in a circle in repeated succession would be a type of simple harmonic motion. But there are several others, something like a spring bouncing up and down, a pendulum swinging back and forth. These two we'll investigate specifically in this unit. Waves, we'll investigate that later in the year. Even things like vibrations of atoms within a molecule can also be modeled as simple harmonic motion. This type of motion comes up over and over again in a wide range of different fields in really physics and chemistry in general. Sometimes this type of motion is what would be called oscillation. If we talk about something is oscillating or has oscillatory motion, that means that it has some sort of repeated motion that's going on over and over again. So two terms that are pretty important when we talk about simple harmonic motion are period and frequency. Period is the time that it takes to make one complete cycle, or do one of that set of motion, or do that motion one time. When we talk about circular motion, a period is how long did it take to go one time around the circle. I use the symbol capital T to talk about period. The units of period should be seconds. Now frequency is related to period. Period talks about how long does it take to do one cycle. Frequency talks about how many cycles can you complete in 1 second. I use the little f to symbolize frequency, and its units are in hertz. 1 hertz is technically 1 inverse second. So the relationship between period and frequency is that they're inverses of one another. Period can be calculated by doing 1 over frequency. Frequency can be calculated by doing 1 over period. If we think about that for a second, if period is how long does it take to do one cycle, and frequency is how many cycles happen in 1 second, it makes sense to say, well, if I have 1 second and I know it takes this long to do one cycle, there's how many cycles are going to happen. If I wanted one cycle and here's how many cycles can happen per second, that's how many seconds it takes for one cycle. So another variable or another quantity that we can calculate with simple harmonic motion is what's called angular frequency. And looking at circular motion, what we call frequency and angular velocity are proportional to one another. Now when I talk about angular velocity, and we'll get into this a little bit more detail later on, it's talking about how quickly something is rotating. So if we think about this frequency, how many times can you rotate a second, and how fast something is rotating should be related to one another. Oddly, this type of angular velocity term shows up in all sorts of simple harmonic motion, even motion that's not circular type of motion. We would call this angular frequency when we talk about it in terms of simple harmonic motion. It's given the symbol omega. It looks like a fancy W. Omega is technically defined as 2 pi times f. The reason for that is 1 time around the circle is 2 pi radians. And so the frequency, really, how many times around the circle do you go? Well, how fast are you traveling or rotating divided by how big is the circle, 2 pi radians. Period would be 2 pi radians divided by how quickly you're traveling. Basically distance divided by speed, or speed divided by distance. In this case, if we wanted to define frequency or angular frequency in terms of frequency, 2 pi times frequency, the size of a circle times how many circles you can do in a second, gives you how fast you're rotating. So this is really the relationship that's interesting. The reason why this relationship is interesting is angular frequency is related to other values when we start to look at specific types of simple harmonic motion. So let's look at a ball rotating around on a turntable. So here I have a circular table, and this ball is sitting on a circular table, and it's spinning around, and I have a series of lights over here, and I have some sort of paper that's going to trace this shadow made by the ball on the paper. Don't ask me what type of special paper this is. Maybe it's some type of photo paper that when the rest of it gets shined by the light, it gets exposed, and you're left with this trace of where the ball shadows were. If we were to look at this trace and actually tear this off and look at it, what you see is something that looks like a wave. And we actually have a function that fits this. It's actually a sine wave. I can call the position x, how far up and down this ball has traveled, or how far left or right this way the ball has traveled, can be modeled as A, the amplitude of this motion, which is how high this value is, times sine of omega t. The omega is your angular frequency. Now if I calculated the velocity, well, I could take, well, what's going to be the slope of this graph and make it the velocity graph. Velocity would be A times omega cosine of omega t. So there's a relationship between velocity and acceleration. Now for those of you in calculus, you might be able to see a second relationship in here that's important. And if I do acceleration, acceleration is going to be negative A times omega squared, angular velocity squared, times sine of omega t. What's important here is that acceleration and position looks like they're related by this quantity omega squared. That actually will become important later on when we start to look at different types of simple harmonic motion. The largest x could be in this motion, or the largest displacement away from the center this is going to be, is just A. The largest v could be is A times omega, and the largest acceleration could be is A times omega squared. The reason for this is the largest sine or cosine ever get is 1, is the largest value they have. So I can actually model simple harmonic motion as a sine wave or a function of sine or cosine. Depending upon how you want to do this, you could say A cosine of omega t, negative A omega sine of omega t, negative A omega squared cosine of omega t, and that would be valid as well. I usually like sine, cosine, and sine. So that's kind of a quick overview of some introduction into simple harmonic motion. What we'll look at in the next lesson is start by looking at some specific cases for simple harmonic motion.